This is lecture number 29. This is a discussion of the design of permanent magnet rotors for both SPMs and IPMs. These are permanent magnet brushless machines that have the magnets on the outside or the inside of the rotor. The purpose of this is to present you the choices, the background, the options before you get around to designing the actual permanent magnet rotor. The main thing in the design is there's two principles involved in the design. First thing is decide which configuration you're going to use. Then do the actual perform the actual design by selecting a magnet and calculating how much flux is going to be produced from the magnet. So there's three choice classes here. One is the IPM design, where the magnets are on the inside of the rotor. Then there's the choice where the magnets are on the outside of the rotor core. And then there's the example where the rotor is on the outside of the stator, these first two choices being where the rotor was on the inside of the stator. So in this case, the rotor's on the outside of the stator, so the magnets have to be on the inside of the rotor yoke. So the part that rotates is this part around here. So you have to decide which one of those choices that are appropriate for your design. Here's a very nice picture that was developed by Professor Tim Miller, and this gives you some of the obvious choices of how to configure these rotors. Here radial air gap machines with the rotor on the inside. This inside, and here's one outside rotor. Okay, we'll just do the outside rotor first. This is a steel magnetic band or cup, can have a flange on it, and the magnets are usually shaped in arcs, and they're bonded to the inside of this, and they're bonded with epoxy or Loctite adhesives. And these magnet grades are nearly always ceramic grades or bonded neodymium grades, unless you're talking about a great big unit like this that you might use in a direct drive wind turbine. Then you could use rare earth in here. Otherwise, in a small machine, you won't have enough space in here to carry the flux of the rare earth, plus wind up with enough room left for the windings. Okay, so let's run through all the inside rotor designs. This one has radial poled magnets. They're radially oriented. When they're put together, they can form a full ring like you see here, or they can be shorter, have shorter arcs and not be a full ring. But you could buy a ring magnet and magnetize it like this as well. It's another point. It could be a sintered or a bonded magnet. And this is a very popular way to make small quantities. It's a bread loaf magnet. You wouldn't probably use this in high volume because there's a little extra magnet cost for the magnet inside here that you don't really need. But this is bread loaf because it looks like a slice of bread, kinda. Looks like cutting the top off of a slice of bread. But this arc is right in the air gap, and this is a flat that's on the rotor core, easy to assemble and bond. Not a full pitch. So this is a full pitch. Take the number of poles, divide it into 360, and that'll give you the mechanical pole angle. Electrically, if you multiply the mechanical angle of this pole arc, you multiply it by the number of pole pairs, you'll get the electrical angle of this. So here's a case where arcs are used to make arc magnets are used. They can be ceramic or neodymium, or you probably wouldn't use ceramic on the OD of a rotor because you wouldn't get enough flux out of it. But these are short of full pitch, and it allows the core to extend out to the OD of the magnets. This gives it saliency. This is like a switch reluctance pole that you have here. So you're going to get a torque from the magnet, and you're going to get a torque produced from the saliency of these steel poles. Now let's look at this one first. This is where you take low-cost ceramic or bonded magnets and you mount them internally to the rotor core like spokes, and these magnets have the shape of being slabs, and they're parallel sided. And this part here, these parts here are soft iron pole pieces, usually laminated, punched from the stator lamps. Cheapest way to do it. you can put a hole or a slot in there to stack them up and support them and assemble them with. It's popular to have little ears of these pole pieces catch the OD, the outside of the magnets, to retain them. Now this is a very common design here, where you could have the magnet in there as a slab, or you can cut the slab in 2 or more pieces and have various shapes in there to get more surface area of the magnet. The next one to look at is an exterior rotor design, which is very useful for applications where high inertia is okay. It helps. It's like an inertia capacitor. Inertia is a capacitor to motion. It smooths out motion. There's an I missing there. That's high I, inertia. So fans and blowers and pumps are good for this. High flux magnet grades are usually not suitable for this unless it's for a large wind turbine. Then you could use rare earth magnets. But smaller motors, you're going to use ceramic magnets because you get a lot of surface area. But if you use a rare earth magnet here, then you got to have enough space inside for the iron to carry the flux in the return path, and enough room left over to put the conductors in. In small motors, that's not possible. Rare earth magnets, you got to use ceramic or bonded neomagnets. Usually the magnets are magnetized radially, but they don't have to be. A real large machine, they could be parallel magnetized. It wouldn't make much difference. You can use adhesive or epoxies to hold them to the yoke. This yoke could be laminated. It could have flats in it to locate the magnets any way. It could have dovetails in it. The magnets can be pre-magnetized and before they're assembled, or they can be easily magnetized after they're assembled, but you need the right kind of a fixture to do it with. They could be magnetized one at a time. You could have a fixture that just clamps around here. You slip this over the top of the fixture and bang, do every other one north, and then reverse the polarity of the magnetizing current, and then do the next ones every other one. You could do that. The yoke has to be magnetic, and it can be made with a mounting flange attached to it on the inside or the outside, and this could be mounted and attached to a die cast or aluminum or zinc part. Now here's another kind of an IPM rotor design that's been very popular. A company in Japan, Fanuc, used to make 40,000 of these a month for servo applications. They're on many CNC controlled machine tools. This cutaway here shows a kind of a comparison between the conventional IPM that has slabs of high energy magnets in it, but this Fanuc design used slabs of low-cost ceramic magnets, $1, $2 pounds for these magnets, and they have very low flux density. They only put out 0.4 Tesla off the surface of the magnet in a closed circuit, but if you put this soft iron pole piece here that's punched out of the hole of the stator core, so you get these essentially for free, other than the cost of the dies, you get them for free. And you see these pole pieces kind of hang over their knots, and they hang over the magnets to support them. And so the area of this pole, soft iron pole, compared to the sum of the two magnet areas is what magnifies the flux. So if this area is double these areas, and it looks like it's at least that, then if I got 0.4 Tesla coming off the magnets, then I got 0.8, 0.9 Tesla coming off of this pole piece. So I have all those lines of flux are focused for higher flux density there. So that's a very popular way to reduce the cost of neodymium or some other version or design of that. The surface, let's talk about some guidelines for designing a surface permanent magnet rotor. These are very popular for generators, permanent magnet generators, and servo actuators. And rare earth magnets are best suited for surface permanent magnet machines because of their high flux density, and the magnets are small because they're on the inside of the stator. Bonded or sintered rare earths can be used as rings, but sintered versions give you they're most cost effective in terms of cost of the magnets versus let's see, dollars per Gauss or dollars per Tesla. Your sinter is probably the most cost effective, but if you take into consideration magnetizing costs and manufacturing costs, some manufacturers will argue that a bonded ring magnet has a net savings to them because of the ease of assembly, and they don't need to have as retainment around the magnets like they do if they use sintered pieces. So full rings or arcs or bread loaves can be used for surface magnets. Magnets can be pre-magnetized or magnetized after assembly, of course. Magnetization is usually radial for ring magnets and parallel magnetization for separate sintered poles. The cores, this shows a solid core where the core is machined as part of the shaft. That's not uncommon for small motors, but you get up to a size where it's reasonable to do it. You don't want to, number one, it costs money on a big rotor. It costs a lot of money to buy a big piece of steel and then spend money to turn a lot of it into chips just to get this shape to mount for a core, to make the core integral with the shaft. That costs a lot of machining costs. So at some point it's cheaper to use the hole out of the stator punching and punch a core out of that, and you can do add a lot of features. You can add cooling features. You can add dovetails or magnet retainment, locating features. There's all kinds of things you can get for free from that. So as the big benefit of using a punched lamination out of the stator is that gives you lamination insulation against eddy currents, which is a good thing. Magnet retention sometimes required to retain the magnets from coming off, particularly if you have some high-speed centrifugal forces or shock and vibration loads that you might have on certain traction motors for cars, trucks, earth movers, and bulldozers or what have you. Now, the IPM motor guidelines have a few different things to consider. These are very popular for traction applications where a wide constant power range is required. It almost always requires laminated cores, although theoretically sintered cores are possible, but probably the tolerance are too hard to hold on the sintered part without machining for the pockets for the lambs. Although I could see you could use a sintered core here and a separate sintered piece and put the magnets on the sintered core and then put this piece on and then figure out a way to hold that, retain that so none of it will fly apart. That's a possibility, use sintered parts. But the magnet grades could be ceramic, as we looked at, if they're V-shaped, or another possibility we'll talk about in a minute. But usually they're rare earths. The part we'll talk about is a combination. You could configure this with a layer of rare earths and a layer of ceramic to reduce the cost of the rare earth. I haven't seen much work done on that, but I expect there'll be a lot of work done. This can be designed, since it's a punching for a core, you can design this with a magnet in a V and get some saliency out of this rotor punching. See, to get some reluctance torque to make this into a hybrid. You get a permanent magnet component and a reluctance component. Magnet retention is almost free in this case using this IPM design, because you have some retention webs here and here that hold the magnet and this mass in place at speed and against vibrations. The rotors can be easily skewed. You can make the magnets in short sections and stack the lambs in the same length, and then you can step skew these groups. So that's good for a good sinusoidal output and low torque ripple. Although a torque ripple with this kind of an IPM rotor is not as serious as it is with the surface mount machines, but you get some torque ripple. Not torque ripple, cogging torque I'm talking about. Cogging torque is not so serious with this because you don't have distinct poles to line up. A little bit, but okay. The IPM designs shapes are very flexible. You can make you can use straight slabs, V's, U-shaped, W's, You can add empty slots. You can have multi-layers to increase saliency. Here's some examples of how creative you can get. Here's a double-layered magnet design, IPM, with big salient poles in between. This was developed, and they even done some shaping of the lamination on the OD to have a variable air gap to improve the sinusoidal back EMF. This is developed by Oak Ridge Labs for traction application. Here's one similar to the Toyota. Some lightning holes in it, like big lightning holes here. This is similar to Ford's design. Here's your retention webs in there to hold this thing together, and there's a kind of a flux barrier. I'm not sure what the purpose of that is, but I'm sure the guy who designed it knows, and he's backed it up with careful finite element analysis. And here's another version that has, I believe this is Ford Motors lamination, and this has got some flux barrier spots in it. This is an interesting one. This is the 2007 Toyota Camry V-shape with salient poles in between. And here's the 2008 Lexus design. Similar, a deeper V, longer magnets, more flux, but then they've added another slab magnet right close to the OD here. And I'm told by Oak Ridge Lab people who have assessed this design, they claim that Toyota's intent there was to add more flux in the centroid to the DE axis to improve the sinusoidal back EMF wave shape. And then here's some lightning cooling holes on the ID. This is another nice picture here that shows the distinctive difference in the IPM. Here's the slab, one slab. Here's the double layer design with a slab and a U-shaped configuration. Here's Toyota's V-shaped configuration. This has a big salient pole. This has saliency due to these magnets and passageways. This certainly has saliency. This is the Fanoop design. That it's a 6-pole version. It's not as effective as an 8-pole version. But here's your Q axis and D axis. There's going to be a big difference in inductance. See, all these show the direct axis and the Q axis on here for D and Q axis current control. And so to effectively administer D and Q axis current control, you determine where the rotor is by measuring these inductances, so that because there should be quite a big difference in the value of the inductance in quadrature axis versus direct axis. So if you can measure the inductances seen by the windings, then you know where the rotor is, and you know where to gate the transistor. So that's what this it shows you where those axes are. Now the torque output for an IPM machine is represented by this equation here. As you can see, it has a lot to do with the inductance ratio, and this is a plot of the sum of the reluctance torque and the permanent magnet torque as a function of current, and you see the phase advance. You have a linear optimum phase advance here to give you that's where the sum of the two torques is the maximum. Seems like it's independent of current. Here's some details to look at for an actual design that you would use. You know, you have to sketch things like this. You need an accurate sketch. You either have to do it by CAD, or you have to have some computer software that has templates that you can do this with. So you can iterate and go through the design, and because you have to pay particular attention to all these dimensions, you have to use some of these dimensions for mechanical stress calculations and other dimensions for magnetic flux calculations. So it's a combination and an iteration of the two. Because when you increase this web, if you put a web in there and increase this bridge, this affects the mechanical stress, the strength of trying to retain this mass at speed. So, but it also provides leakage paths for the flux to go from you getting the magnet. So you have to go back and forth and calculate that. Then this web thickness here, or the salient pole width, is very important to calculate and determine what the reluctance torque component is. So So it's very reiterative between the dimensions of the mechanical issues and the magnetic issues. Here's a very interesting concept of another flux focusing or use of low-cost magnets. This is a design, very clever design, designed by a company out west called Rotor, and they use a dual cone rotor, one on each end of the shaft. There's one on this end of there's a shaft. There's another one of these on this end, and the pole pieces are soft iron, probably sintered, either laminated but probably sintered. You see, and those are flux concentrators. Now here's slabs, very low-cost slabs of ceramic magnets. And these ceramic magnets only put out a flux density of maybe 0.4 Tesla. And with the cost of magnets, you could see here's the cost of ferrite, relatively flat, compared with the cost of neodymium. Even when neodymium was down here, this was a good idea. But now that neodymium has gone way back, even though it's coming back down, why, there's a tremendous cost advantage with very little, if no penalty in performance by using ceramic magnets like the Fanuc motor, and this is a special version of that where you have you not only have the flux focusing advantage of these soft pole pieces, but the cone shapes also gives you a flux density focusing advantage, because the cross section of the stator is in this plane. So, but you get the flux density here is probably if this is 0.4 Tesla, the flux density across there is probably 0.7 Tesla, and by the time it's in the steel pole of the stator, because of the cone shape, it's probably 1 Tesla. So I don't know what it is, I haven't calculated, but that's the idea of this flux focusing. Very clever, give you some ideas. It is patented, but there's variations of these kind of ideas that you should be thinking about. Now, this is a discussion about cogging. Cogging torque is an unwanted characteristic of any motor with permanent magnets in the stator or the rotor. If the edges of the magnets line up with the slot openings, those become detent positions. Those are cogging points, and those are undesirable for a variety of reasons in a variety of applications. Some applications doesn't matter, they don't care. But some applications it does. Some applications this cogging torque has to be way down in the 3rd, 4th decimal point. It's got to be very low. Well, the simplest way to reduce that, there's 2 simple ways. One is to shape the pole of the magnet and put radiuses on the rotor to give you a variable air gap. That helps a lot. Okay, but there's penalties to pay for that. Some people don't like to do that. So another way is to skew the stator. I can take the stator and skew it when I assemble it. That's a possibility. The other way is to skew the magnets. Now here's a case where I've got individual centered magnets and they have to be tooled that way. Okay, that's not so happy. Here's a case where you have a bonded ring magnet and it's magnetized skewed. That's a very good way to do it. Another way to use low-cost, simple magnets is to skew them like this. Skew them like a stair step. Make sections of the magnets. It's advisable to do that anyway, because by breaking this pole up into several segments, you segment it and insulate it against eddy currents. We'll look at that later. But so you could stair step those like that and have the effects of skew. And the other benefit this does, besides reduce cogging torque, it improves the sinusoidal back EMF significantly. Here's another example of what I was talking about, of this stair stepping of the actual magnet. Here's the North Pole, there's the South Pole, but it's made up of several magnets, so I step it. Here's one that's done in 2 steps. To measure the cogging torque, you can use a torque watch. You could buy these, they're a few $100s, and you buy them from Honeywell. It's a very good device to use to actually measure them on a dyno. It's very tough. You need a torque transducer in line, and you've got to rotate this very slowly. But so I think the torque watch is a good method. The design process for the machine, for the rotor, is going to take place after you've made all these machine sizing decisions that we talked about in this chapter, and we talked about in the other chapters of sizing and windings. We studied all those things, material selection. We studied those topics that are applicable to all the motors, and they certainly apply to this one. The one thing that you have to decide how this motor is going to be driven. It's going to be driven as a 6-step motor, or you're going to have sinusoidal current control, either using hysteresis method, or you're going to use the D and Q axis current control. And then you got to know what's the maximum PWM frequency the inverter guy can deal the losses with, the switching losses in his transistors, because that determines the max number. You always want to use the max number of poles, as I've iterated several times. So after all those decisions are made, what you have to do is determine what the flux is you're going to get with the magnets. How much leakage flux, estimate what the leakage flux is. You can do that, but the finalization of that's only going to come from FEA analysis. But the initial flux estimates are essential just to proceed with the stator design, because stator design's got to know how much flux it's got to carry, plus the winding space required for the number of turns in the wire gauge. So the first thing you do is determine what the working load line of the magnets in a magnetic circuit are going to be with an air gap. That is the best way to do that, is to get a BH curve from the manufacturer and then plot the load line on there, which is permeance coefficients, and graphically figure out what the flux in the gap is going to be. And there are some leakage coefficients as well you can use, but you can ignore those initially. The air gap thickness you're allowed, you've got to decide on that too. That depends on the manufacturing process. The core of the stator is usually never ground. It's as stamped, so the tolerance on that is in accordance with the manufacturing and stacking tolerance, which is probably within plus or minus a couple thousandths of an inch. You can rely on the ID of the stator. If there's a magnet retainer sleeve required over the magnets, the mechanical gap has got to be big enough, or the magnetic gap has got to be big enough to have room for the sleeve, plus have a mechanical gap over the OD of the sleeve, so that the windage or the air friction in the gap isn't too high from the rotor spinning inside the stator. High-speed machines, that could be an issue. So the magnet open circuit load line, or the permeance coefficient, is a ratio of the magnet's thickness to the magnet air gap dimension. So the useful flux from the magnet depends on this load line. So the peak demagnetization current allowed by the stators depend on this load line. My recommendation is never design a permanent magnetic circuit with a permeance coefficient less than 3, and go with 5, 6, 7, 8, 9, 10 if you can. And then of course you have to study the demag as well. Now here's what I'm talking about. Here's a BH curve, a set of BH curves at different temperatures, 20 degrees C, 60, 100, 140 degrees C, for a particular permanent magnet grade. And the permeance coefficients are given up here. So if you know that your magnet thickness is twice as thick as your air gap, that's a permeance coefficient of 2. So to determine the load line, you would take a straight edge and put it through the ordnance, and you would go up here and line it up with 2 and draw a load line. Draw a load line there. In this case, we have a load line there. That's drawn for if this scale doesn't have a good enough resolution, just plot the air gap on the X scale and plot the magnet on the B scale, and draw some lines to intersect those. And where they intersect, that's where your load line is. So that's your permeance ratio, is where these two intersect. So you draw a load line from the ordnance through that intersection point, straight out here, and where it intersects these BH curves, you project over to the B scale, and you read the flux there. So at 140 degrees C, you're going to have this much flux. At 20 degrees C, you're going to have this value of flux. Okay? Now, if you were at 20 degrees C and you had no air gap, remember our example of the C yoke, you would have 1.4 Tesla. But with this particular air gap, a reasonable air gap, at 20 degrees C, you've only got, 1.1 Tesla instead of 1.4. So it required that much. That's what you lost to drive the flux across the air gap. That's really what it boils down to. Now, as the temperature goes up, that goes down. So you use the normal curve. That's these curves. The dotted curve here, and every BH curve plot you get has these dotted curves, and you see that this magnetization of this magnet goes through all four quadrants. This is the second quadrant. This is a demag curve. This is where the operating quadrant of the magnet in a motor. That's why this is the one we look at. But the demag of these materials doesn't show up at 20 degrees C. It doesn't show up in the second quadrant. It does show up, the knee of the serve does show up in this quadrant at higher temperatures, but it doesn't show up at 20 degrees C. So the data in the third quadrant is converted to be plotted and displayed in the second quadrant so I can use it there. And that's what these values are. That's a new plot of the sum of the BH values for every point on these curves is plotted up here. So I've converted the third quadrant BH curve into the second quadrant so I can analyze it for demagnetization. And we'll look at how you do that later. I think we already went over that in the magnet section. But so that's how you determine the flux density, is plot the magnet thickness in the air gap on this curve and project over and read that data and write that down. And then you can adjust the permeance coefficient. If you have a lot of slot openings, there's a technique using Carter's coefficients. You'll see that here. But for your first estimate, you don't even have to do this. If you're going to finalize your design with a finite element analysis, it'll take all that into account anyway. You don't have to mess around with Carter's coefficient. But at any rate, you can use that if you want, and this explains how to do it. But after you've got that far, here's a slide on pole shaping. If I make the shape of the pole different than the circle around the poles, I have a tapered variable air gap. You can see the difference of tapered gap. That's a way to get the effects of reducing cogging and be more sinusoidal. But you see, you've now changed the air gap. So which air gap do you use in that formula? You have to use some average of the max and the max air gap and the minimum. It's best to use that in determining your permeance coefficient. Here's some examples of some IPM rotors. This one is the Ramey motor with 2 layers of magnets with big salient poles in between for reluctance torque. This is the Ramey motor using a Chevy Volt, and this is a single layer magnet with a flux barrier right in the center of the 2 magnets, and here's your webs that support this whole together. This is the motor used in the Ford hybrid vehicle, and these holes in this is so they can stagger in a stepwise fashion. They skew sections of this. That's what these holes and those sets of holes are for. Some of these surface magnets, you have to use high strength metallic retention sleeves, or shrink fitted or pressed, or a combination of both. And these need to be designed carefully. They have eddy currents. You got to do mechanical stress calculations, and then you do magnetic loss calculations as well. Finite element's the best way to do that. You can retain them with the dovetail magnets that I showed you. I think I showed that. If not, it's coming up already. But for high-speed stuff where eddy current's a problem and you need high stress, you can pre-stress wrappings around the magnets, either fiberglass, Kevlar, or carbon fiber. It's easy to assemble and disassemble magnetized rotors if there's a wrapping over the magnets as well. This is a dovetailed example. So if you're going to punch the rotor out of the stator core, you could punch it with these shapes, so you don't have to tool the accurate positioning of the magnets, and these dovetails hold the magnet in place, so you don't have to wrap it. That's not a bad way to go. You can use pre-magnetized magnets in that. Here's a couple examples of a carbon fiber, pre-stressed carbon fiber. These were made by E&A in Switzerland. This is one that I built myself. It's 40,000 RPM, 100 kilowatt machine tool spindle used for spar mills. Boeing's got several of these, and Airbus have several of these. This is for high-speed machining of aircraft parts, wings on 747s and things like that. But the speed's so high and the stresses are so high that we use a carbon fiber for that. But these are the materials that are optional. Inconel 718, 301 stainless, titanium, carbon fiber, Kevlar fiber, or fiberglass fiber. And the fiber ones need to be wound in tension and then held in place by epoxy or pre-impregnated fibers with high temperature thermoplastics. Here's a plot of a 50,000 RPM spindle, which was this one. It operated at 40, but it was designed for 50. You have to have a conservative overspeed. And here's the plot of the analysis we did to look at different rotor diameters over the magnets. These are the retaining mass diameters, and with a fixed magnet thickness, so that we plot here the thickness required for the pre-stressed sleeve at different diameters. And there's two curves here, one for a pre-stress of 150,000 psi and 175,000 psi. That's how much you stretch the yarn. That's the stress you put on the yarn. That's not the strain. That's the stress on the yarn when you wrap it over the magnets. Here's an interesting plot that shows the flux distribution using FEA analysis of a 10-pole 12-slot motor, which is a design that's been developed to get around a tough patent on a 12-slot 8-pole machine that's owned by Pabst in Germany. They've sued everybody and won every time, and this is a 10-12 pole a patent design around. I first announced this in my first book in 1990, but there's some patents been issued on it by the Japanese and the Americans, but they're not defensible because there's prior art described in my book. But you could see the difference in the flux paths from the IPM versus the surface mount. I think that's good for you to have in your mind. Here's a unique permanent magnet rotor. This is not done with magnets, it's done with permanent electromagnets. And these are special coils that you get the current to flow in those, and while it's at minus some 73 degree Kelvin or 173 Kelvin or something like that, so that the resistance there is zero, so the current never decays. So that's essentially a permanent magnet. That's superconductivity. So that concludes this this introductory lecture on the issues regarding the design of a permanent magnet rotor for brushless machines. Thank you.